In our previous video segment, we looked at factors that affect solubility, and we're continuing that discussion in this video. We introduced already the most important of the factors that affect solubility, which is the chemical structure of the solute and the solvent. I introduced the concept of like dissolves like, that solutes with similar polarities to their solvents, therefore similar intermolecular forces of attraction, will more readily dissolve in each other. So polar solute dissolves best in a polar solvent. A nonpolar solute dissolves best in a nonpolar solvent. Now let's take a look at the second of the factors that affect solubility, which will be discussed in this text, and that is temperature effects. Notice I'm breaking temperature effects into two different categories. Solutes can be either solids or liquids or gases. So we're going to look at temperature effects involving liquid and solid solutes, and then consider temperature effects involving gaseous solutes. So if we're looking at how temperature affects the solubility of a liquid or solid solute, you see the statement that increasing temperature usually, not always, but usually, increases the solubility of liquid and solid solutes. If you have your textbook, you might want to look at page 321, figure 9.5. This is a solubility curve showing solubility in grams of solute per 100 grams of solvent on the y-axis in an increasing order, and temperature on the x-axis in increasing order. It shows the solubility of various ionic compounds as a function of temperature. And I've drawn the curve for only one of those ionic compounds, potassium nitrate. And you can clearly see from the curve the illustration of the principle we just stated. As temperature is increasing on the x-axis, solubility, how many grams of potassium nitrate dissolve in 100 grams of water, is increasing on the y-axis. So solubility of potassium nitrate increases as temperature increases. We can obtain information from a solubility curve to do various sorts of calculations. For example, if you take 121 grams of potassium nitrate and mix it into 175 grams of water at 40 degrees Celsius, A is the resulting solution a saturated or unsaturated solution? How would we solve that problem? Well, first we are going to need to read the solubility of potassium nitrate at 40 degrees Celsius from its solubility curve. So, drawing the curve as best I could, temperature at 40 degrees Celsius, coming over to the y-axis, I see that the point is a little bit above the 60 line, in between the 60 and 80 line. So I'm estimating here the point of the curve definitely is closer to the 60 mark rather than the 80 mark. So using some estimating, I am reading the solubility of potassium nitrate at 40 degrees Celsius to be 63 grams of potassium nitrate dissolved per 100 grams of water. And of course we know that the uncertainty is in the ones place. That's the value that we're estimating. Could be 64 grams, could be 62 grams, but that's a reasonable estimate for the solubility of potassium nitrate at 40 degrees Celsius. What can we do once we have this solubility value? Well, the problem told us that we had 175 grams of water. So we can use this solubility and answer the question, if you have 175 grams of water at 40 degrees Celsius, And the solubility of potassium nitrate is 63 grams per 100 grams of water. We can use that as a conversion factor and calculate how many grams of potassium nitrate can dissolve in 175 grams of water. So all those dimensional analysis skills that we learned at the beginning of this semester are coming back to be useful for us here. Our grams of water are canceling. We're left with grams of potassium nitrate. And doing this calculation, which I did, but let's just go ahead and double check. 175 times 63 divided by 100, and I get 110 grams of potassium nitrate can dissolve with 2 sig figs in 175 grams of water at 40 degrees Celsius. Well, the problem told us that we had 121 grams of potassium nitrate mixed with 175 grams of water. So just doing the comparison, 121 grams of potassium nitrate is present in the mixture, but only 110 grams of potassium nitrate can dissolve. So clearly we have more solute present than is able to dissolve. So if we stirred, what we would get as a result is a saturated solution of potassium nitrate. There would be undissolved potassium nitrate present at the bottom of this solution container. So we could also answer question B. How many grams of undissolved potassium nitrate is present? And this should be a simple subtraction of the amount of potassium nitrate we added that is present and the amount that dissolves. The only tricky part is the sig figs. So when you do that subtraction, you get an answer of 11 grams of potassium nitrate. But remember, that uncertainty is in the tens place. So expressing this with the correct number of significant figures, 1 times 10 to the first grams of potassium nitrate would be present as undissolved solute. As undissolved solute. Now that we've looked at how temperature affects the solubility of liquids and solids, let's consider how temperature affects the solubility of gaseous solutes. Different story entirely. Increasing the temperature always decreases, not usually, but always decreases the solubility of gases dissolved in solution. And why is that? Kinetic molecular theory tells us that if we increase the temperature, we're increasing the average kinetic energy of gas molecules. They're moving faster in solution. And if they're moving faster, that favors them breaking free of the intermolecular forces of attraction that hold them in solution and moving them to the free gas state above solution, where they're not interacting with each other at all and essentially have no intermolecular forces of attraction. So increasing kinetic energy of gases favors them escaping from solution. You can take a look in your text. Also on page 321, they illustrate this effect, showing a solubility curve for 3 gases: oxygen, carbon monoxide, and nitrogen. And we see that as temperature increases on the x-axis, the solubility of all of these gases decreases as temperature increases. This creates an issue of thermal pollution, which your text mentions. We have traditionally wanted to build our factories next to lakes and rivers and use the water from a lake or river to cool the factory, the machinery, the engines that power the factory. The problem is that heat from that factory can get transferred or will get transferred to lakes and rivers if we use their water to cool our factories. Well, as heat gets transferred, temperature goes up. And as temperature goes up, the solubility of gases in the lakes and rivers go down, particularly the solubility of oxygen gas, which is needed by fish. They have to breathe, quote, just like you and I do. They have a respiratory system that is equipped through gills to remove the oxygen from water. But if we have dropped the solubility of oxygen in the water because we've heated the water up, then there is less available oxygen to support aquatic life, and this is harmful to them. So we are trying to make progress with dealing with the issues of thermal pollution by making sure that factories have their own cooling ponds with which to cool their machinery and not relying on natural aquatic systems to do that, the water present in them to do that. Let's take a look at the third of the factors that affect solubility that we will discuss here in this text, and that is pressure effects. Again, separating pressure effects into two different categories. If we look at how pressure affects the solubility of liquids and solids, we see not that much of an effect. Increasing pressure has little effect on the solubility of liquids and solid solutes. Why? Because liquids and solids are already compressed states of matter, and increasing the pressure cannot drive them into solution. There's no empty space, quote, to squeeze out and force them in closer contact with solvents. With gases, it's a different story. Notice that I'm mentioning Henry's Law here, not a name that you need to remember, but this is a statement of Henry's Law. Increasing the partial pressure of a specific gas above a solution increases the solubility of that specific gas in the solution. And an example is carbonated beverages. If you enjoy a carbonated beverage, you enjoy the fizz effect that happens when you open the can. And that fizzing is the result of carbon dioxide escaping out of solution. Well, how did it get there to start with? And the answer is in the bottling plant where the carbonated beverage was bottled. It's bottled in a condition where there is a high partial pressure of CO2 above the solution that is being carbonated. So the soda that has the flavorings and the coloring, etc. You put it in an area with a high partial pressure of carbon dioxide. Lots of carbon dioxide above solution. And that high partial pressure of carbon dioxide drives carbon dioxide molecules into solution, to dissolve in solution. And then you bottle off or seal off the container. And then when someone opens that container at home, all that CO2 that was driven into solution escapes out because the regular atmosphere has a very small concentration or partial pressure of CO2 in the regular atmosphere. So all that CO2 that was driven into solution escapes out of solution into the regular atmosphere once the bottle is opened, and that creates that fizzing effect that we see with carbonated beverages.